Let's keep it rolling here. 5. 5 and 6. Derivative time, right? All right, so you have some options here. Yes?
What are those things called again when you have infinity times 0? Like
Indeterminate forms. Mm-hmm. And that will be on the test. That'll be in the L'Hopital's rule section. All right, derivative, step 5. Now, I didn't call this f, but let me call it f of x. All right, so first derivative of this function is, yeah, there's a couple of ways. I'm just going to go product rule. Is that all right with you? Product rule? Right here. Derivative of the first one is 1 times the second one, plus derivative of the second one. So let's be careful on that. Derivative of root of something, 1 over 2 root of the something, right? Times the derivative of what's inside, -1, and then finishing off the product rule times x. Agree? Yeah, this is going to be root 5 minus x, and then minus x over 2 roots of 5 minus x. What am I going to need to do with that eventually here? Set it to 0. And so since one of those is a fraction, I'm just going to turn this whole expression into one big fraction. And to do that, I'm going to need a common denominator. Well, LCD. LCD. So I'm going to look at this as being a fraction minus a fraction. So I will need to multiply that first fraction on the top and bottom by 2 root 5 minus x. So I'm going to do a 2 root 5 minus x here, multiplied on this top one, and then same thing on the bottom, 2 root 5 minus x. And so my new numerator here, I'm going to do a little, well, go kind of slow. There's 2 5 minus times 5 minus x, right? The 2's there. This root times this root, the roots go away, you have 5 minus x. But the 2 has to distribute to each one. That's the new top. That's that new top. And then now, why don't I combine it with this top? So minus x over the common denominator, which was 2 root 5 minus x. And now distribute and collect and get 10 minus 3x. Good. Over 2 root 5 minus x. There's our, yeah, that's a pretty clean version of the derivative, right? So take our derivative and set it to 0. Ten-thirds? 10/3? Is that in our domain? Yes, it is. 3.3 something, right? 3.333. That's in our interval, so we're good. Now, I also need to look where the derivative is undefined. Does this ever not exist? Yeah, we already know that there's a domain restriction, right? We know that we can plug in negative infinity to 5 can go into the original function, right? But in the derivative, I actually can't plug the 5 in. Like here I can plug 5 into the original, but here I can't plug in 5 because of what? You get division by 0, right?
Wouldn't that be a limit?
What do you mean?
Because you can get like, you can plug in like 4
Okay, I get you. Yes, that's if I was interested in knowing what this derivative was doing. My guess is that it's going to become, if you start taking that limit, if you did, it would become like infinite, which means the slope of the tangent line is becoming vertical. But all that's important to us is that x equals 5 is an interesting point, right? It's an interesting point because it's a place where my derivative is undefined. I don't need to consider anything else because I'm locked in here, right? I can only be in here because of the original function's domain. It makes no sense for me to look over here at 6 or anything else. All right, now a number line, right? No questions? What goes on this? I've got 10/3, which is 3.3 forever, and 5 is to the right of it, right? This would split up my number line. I can put boxes around these because they are part of our domain, but I only have 2 test points. Something here, and then over here, I'm not even allowed to go here, right? I can't even go into this region. It's not part of the domain of the function. So what are some good points here? 0, I like 0, and 4. And those get plugged into the derivative, which I just erased. 10 minus 3x over 2 root 5 minus x. Okay, so 10 minus 3x over 2 root 5 minus x. That was our derivative, and I get to plug in. So how about 0? Positive on top, positive on bottom, increasing. Plug in 4. Negative on top, positive on the bottom, decreasing. Do I have a local max or a min? Yes, local max only, right?
So then we need to plug it into the next.
Yep. Where is this function increasing? Negative infinity to 10/3. Where is the function decreasing? 10/3 to 5. We have a local max. It happens at 10/3. And now I actually have to plug 10/3 into the original function. So what would I get if I plug 10/3 into that function? Let's see. 10/3 square root of 5 over 1 minus 10/3, because I'm about to subtract those. That's 15/3 over minus 10/3, so 5/3. Root 5/3. I don't think there's any easy way to get out of that. Calculator time. You got what?
I got like 4.3.
4.3? Okay, so we'll use a decimal, okay? 4.3 something, approximately, all right?
Approximately, yes. Because it was like 4.29.
Just, what did I do here to go from here to here? Just curious. Push those both into the root, right? Push in the 10, it squares on its way in, becomes 100, then hits the 5, becomes 500. 9 goes in, gets squared on its way in, becomes a 9. 9 times 3 is 27. That would just be easier for me to type into my calculator. I just do 500 divided by 27, and then I take the square root. But you get about 4.3. All right, second derivative time. All right, I need to put my derivative back up here. 10 minus 3x over 2 root 5 minus x. Oh, man. Do you already see this is going to not be fun? This is the suffering I'm talking about. We have to take that derivative and we're going to have to clean it up and set it to 0 and all that fun stuff, right?
Do we do property of logs?
To do logarithmic differentiation,
Yeah.
I suppose you could.
It would try to get it away from a quotient rule.
Then you'd have to go back and multiply that.
Then you'd have to multiply that at the end. I don't know. I'm actually in favor of that. Does everyone understand you could do quotient rule right here? You could? But I kind of like the idea of calling this thing, let's call this thing anything we want. But I won't call it y, because that's y. If I call this m, is this, and we're asked to take the derivative, then I could do natural log on both sides first. Couldn't I? Natural log of m equals natural log of 10 minus 3x over 2 root 5 minus x. And then I could use the property of logs to split the right side into what? Natural log of 10 minus 3x minus natural log of 2 root 5 minus x. You could do quotient rule, all right? I'm okay if you do that, but I actually do think this is going to be easier to work with. Well, but we have to set it to 0. Minus, watch, natural log 2 minus natural log 1/2 natural log of 5 minus x. What the hell just happened? This was a product, right? I split that into 2 logs with addition, but the minus distributes to each one. Then, when I had this log, natural log of this root, I set to the 1/2 power, and the 1/2 came out right here. And then we would take the derivative. So what's the derivative of the left side? Implicitly. 1 over m times m prime. What's the derivative of natural log of something? 1 over it, chain rule, times derivative of what's inside, m prime. And then what's the derivative of natural log of this? 1 over this times derivative of what's inside, -3, right? So -3 over 10 minus 3x. What's the derivative of this? This is a constant. Isn't that a constant? Natural log of 2? That's just a number. So derivative of that is 0. What about this? Minus 1/2 comes for the ride. What's derivative of natural log of 5 minus x? 1 over it, but then times derivative of what's inside? -1. So -1 over 5 minus x. So here's where we would be. 1 over m prime equals -3 over 10 minus 3x plus 1 over 10 minus 2x. I just distributed this through. 2 went to here and here.
Oh, we're so close. It was almost crazy.
Almost, but now we have to multiply both sides by what? By m. Right? We have to multiply both sides by m. I still think we're okay. When I multiply both sides by m, I get -3 over 10 minus 3x plus 1 over 10 minus 2x. All of that times what? M, but m was 10 minus 3x over 2 root 5 minus x. Is that all right?
Probably better than doing quotient rule.
I don't know. I mean, I'm still okay. Are you still working on the quotient rule there? Okay. So there's the derivative if you use logarithmic differentiation instead of quotient rule. What are we going to need to do with that derivative? Set it to 0. So does everyone agree that this is f double prime of x? Okay. So if I ask you, where is f double prime of x 0? You're going to set, look at, it's already factored, isn't it? Two things. So I have to set this to 0 and this to 0. Now this can only be 0 when? When the top is 0. So I have a couple of things I'm looking at here. 10 minus 3x equals 0. That's one thing I have to look at, right? Now, when would this thing be 0?
Well, you might want to try and put a LCD.
You're going to have to get a common denominator there. So you're going to have to multiply the top and bottom of this one by that, and the top and bottom of this one by that, to put those together. So what would happen if I multiply negative 3 times this? Negative 30 plus 6x. Okay, plus, now what happens if I multiply 1 times that one? 10 minus 3x over those things together. 10 minus 3x and then 10 minus 2x. And clean up that numerator.
So this is 3x minus 20.
3x minus 20?
Yep.
So 3x minus 20 over what? The common? Right? The common denominator? This thing? Did I lose you all? Did I lose everyone?
So when you just set the top,
So you're just going to set the top equal to 0, right? That's why I didn't fill it in. So I need to set 3x minus 20 to 0. Which means, well, I'll solve that in a second. Is that good? This became this, and I'm just going to look at the top when it's 0. That's going to happen over there. So solve both of those. We should get 10 thirds again. Is x, and then over here we get 20 thirds.
isn't it negative?
No, because you move this over.
Yeah, you divide by negative 3.
When you move it over, it's positive 3x,
Yeah, there you go.
and then divide by 3. Yeah? Okay. This one, move the 20 over, it becomes positive 20, divide by 3. I'm going to chunk this one. Why? It's outside my domain. 20 over 3 is 6 something, so that's outside. 10 thirds is in my domain, so I've got that one. Now we also have to look at where the second derivative is undefined. Where does my second derivative not exist? Are you still working on derivative there? Or?
No, I'm just checking it.
Okay.
I messed up.
Okay. And now let's figure out where this thing would be undefined. So I'm going back up to this, or I could look at this one, it doesn't matter. How about this one over here? Where is this undefined? At 5. So 5 is a critical number, but that's the endpoint, right? X equals 5. And what about this? That could be undefined, couldn't it? If x was what? 5. Right? If x was 5. What about this one? Uh-oh.
3.333. 1/3.
That would also be at 10 thirds,
Also not.
wouldn't it?
Yeah.
So I've got a major issue happening at 10 thirds. It's looking like I'm getting something like, Oh, I see it, I see it. You know what I didn't do right here? See this guy right here? Did y'all see that? I forgot to do that algebraically. But 10 thirds is still an important number because we're getting like an undefined thing happening. It's like a 0 over 0.
So that would take that away on that side.
Say again?
That would take that away over there.
I'm still going to look at 10 thirds because it's somewhere where my numerator and denominator looks like they would be 0, right? Oh boy, what a mess. Do we want to do it with the quotient rule just to see it, or are we happy?
Yeah.
Yeah, we're happy, or yeah, you want to see the quotient rule? You want to see the quotient rule? Okay, let's see if we get the same results. I'm going to work pretty quick though. I'm doing quotient rule on this. Derivative of the top times the bottom minus derivative of the bottom. So there's a 2 there already, right? And then 1 over 2 roots of 5 minus x times inside derivative is negative 1 times top 10 minus 3x. I'm redoing the second derivative again by request, but using quotient rule instead. So I'm doing derivative of the top times the bottom minus derivative of the bottom. 2 is a constant, comes for the ride. Derivative of root of something is 1 over 2 roots of that something. Derivative inside the root is negative 1 times the top, boom, all over the bottom squared. Right? All over the bottom squared. 4 times 5 minus x. And now, cleaning here, this 2's cancel. Negative and negative become plus, right? See that? So I'll have negative 6 root 5 minus x plus 10 minus 3x over root 5 minus x all over 4 times 5 minus x. Common denominator. Right here, between these two. So introduce this root here and here. So you get negative 6. Then the roots will kill each other off. You'll get a 5 minus x there. Then I have plus this, plus 10 minus 3x, all over root 5 minus x, all over 4 times 5 minus x. And I think I'll even make this a fraction over 1 because I'm about to take it and flip it like this on my next line. What do you get if you clean up the top? I sure as heck hope it's something like negative 30 plus 6x plus 10 minus 3x. Isn't it that one?
Yeah.
It's going to be that. So we get 3x minus 20 on top over, and then flip that like this, right? And so the only thing left on the bottom is 4 times 5 minus x times root 5 minus x. I actually like that better than the logarithmic differentiation personally. Just for this problem. That's a pretty clean derivative. Questions? What's interesting, I think, is that on the logarithmic, we actually got a critical number that we didn't get here. But when we actually test it, if we were to do this and test both sides, we're not going to get a change in concavity. It's just going to stay the same. But it's interesting that we got it. Because what are the critical numbers here? 5, right? Gives you division by 0. And then the top, we already did that. It's outside of our domain. So we would have no critical numbers, right? All you would have is 5. All right. May I erase? All right. I would go to the next step, which would be a number line. Weird thing is that if we do it with the quotient rule way, then the only critical number we would have would be 5, right? And we're not allowed to look over here. So what do you do? No, I'm saying if we didn't do the logarithmic differentiation, we would have no critical numbers. We just pick any number. Because what this would tell us is that our concavity never switches. It's always the same thing. So it's either always concave up or always concave down. So we pick any number we want, as long as it's in domain. So how about 0? Let's plug in 0. And we're plugging that into the second derivative, which was 3x minus 20 over root, all that stuff. So if you plug 0 into that second derivative, you'll get a negative number. And that means it's concave down. Now, like I said, if you would have put this 10/3 on here, and you tested 2 points on both sides, you'll get concave down on both sides, which means that there's no change in concavity, there's no inflection point.
That's strange how the logarithmic differentiation is.
Yeah, I think that there was something that should have canceled, but I mean, algebraically, that looks like everything was done right. I did it kind of quick. I'll go run back through it and make sure I didn't miss anything, but it all looked okay to me. All right. I think we're ready to draw it. Yeah? Oh, where's this thing concave up? F is concave up. Never. How do we say never? In interval notation. Empty set. Empty set. Yeah, this is the empty set right here. It's a set of nothing. And then where is it concave down? On its entire domain, right? Which is this. And you can do the bracket or the parenthesis, but I always said just do the parenthesis.
So, the other one was wrong.
Which one?
Because at the beginning you did it.
No, because, no, if you put 10/3 on here, and you test both sides, you're going to concave down on both sides. So you're still going to get the same result at the end.
The local max.
But yeah, 10/3 is where we have something happening. But that's from the first derivative, right? The local max is happening there. All right, I'm ready. No inflection points, right? No inflection points. Do I only have like, what, 10/3 is the only number I have on here?
10/3.
F prime, F double prime, F. All right, it was up, then down. It was always concave down. And that means we have to be going up, left side, down, right side. This is going to be a lot of work for a pretty simple looking function when it's all said and done. Number line, 10/3, 5, and now we start putting everything together. So domain, my picture should only exist this way. I had an x-intercept where? 0, so 0 would be over here, wouldn't it? An x-intercept there. I also had an x-intercept at 5, didn't I? And the y-intercept was actually the same as the x-intercept, so over here. Did I have any symmetry? No. Did I have any asymptotes? No, I just know that I went out to the left, it went down to infinity, right? Do I have local max? At 10/3, and then what came out? 4.3? So if I go up to 5, 1, 2, 3, 4, so 4.3, somewhere around here. That's ballpark right there. And inflection, nothing, right? So all that for this. To the left of this point, right, it's supposed to look like that, and it's going to pass through that point. So it almost looks parabolic. And then on this side, it's going to do kind of the same thing. Like that. But it's not exactly a parabola because this stops here, doesn't it? It comes to an end. It is a lot of work. Especially when you can just go walk over to the computer and type it in and have it graph, right? All right, I don't have time to start another problem. Like I told you in my other class, I did a problem that had trig in it, which is like the one you have here for 4. So you might want to go take a look at that one. And these are due on Tuesday, right? These are due on Tuesday. There is a homework set for this section. There is a homework set, but I recommend that you start on this. And if you get to the homework set, you get to the homework set. But I don't think there's anything that you could do in the homework set that's going to make you any more prepared for these than just going after these, you know? So you may as well just look at this as being your primary homework for now, for this section. And that's it. I have nothing else in 4.4. On Thursday of this week, we will, hold on a second. I need to check my calendar for something. Well, you know what? We're a little ahead of the game.
Is that good?
Well, we have mean value theorem. So why don't we do this? Work on your sketching. We'll come in on Thursday. We'll do mean value theorem. We'll just look at it, and I'll talk more about sketching in the test. So Thursday is going to be kind of like a more chill day. The mean value theorem will be pretty quick.
Is that going to be on the test?
Why don't we talk about it as a class? Maybe what I'll do is I'll offer that as like a bonus question. I'm thinking that's what I could do. Just throw it in as a bonus. Yes?
You can put some more problems up on the board that we can work out as groups and kind of.
Problems like, just like from test, like just like random test problems?
Like how you did last time, 'cause I found that kind of helpful, just working with peers and
Yeah, we can do that. We can get through the mean value theorem. Once that's done, I can just say, hey, y'all want to work on some problems in here. Let you work on them. Okay, yeah.
Wish you had a review still.
What's that?
I wish you still had a review.
You wish I had a review. Well, we'll do some form of